You know, it's really struck me lately just how much the whole landscape of science in the US has shifted just since the beginning of 2025.
Oh, absolutely.
It feels like every week there's some new breakthrough. Medicine, space, physics, biology, tech. It's across the board.
It really has been an incredibly dynamic time. The pace, the sheer velocity of discovery, it's quite something.
Yeah, and that's exactly what we're digging into today. We've basically waded through, well, a mountain of sources, articles, reports, the whole nine yards, all to bring you the most sort of compelling insights, the key takeaways on where American science stands right now. Think of this as your shortcut to getting up to speed.
Right. Our mission here is to give you a clear picture. What are the big scientific leaps forward? How is research funding changing? And crucially, what's happening with the science policy that shapes everything?
And we've pulled from a real mix of sources to try and give you that well-rounded view.
Exactly.
Okay, so let's dive right in. Medicine, that's something that affects everyone. And wow, the progress seems relentless.
It really does.
Yeah.
We've seen some genuinely remarkable strides. Take gene therapy. There's work at University College London focusing on drug-resistant focal epilepsy.
Okay.
They're using what's called a viral vector, basically, a modified virus, to deliver the LGI1 gene. The idea is it helps regulate brain cell activity.
So it's delivering the fix biologically instead of, say, surgery.
Precisely. It could be a real alternative, especially for patients where surgery isn't a good option, which is often the case.
That's huge. And it kind of highlights that move towards more precise treatments, doesn't it? Like with CRISPR. We're hearing about CRISPR 3.0 now.
Yes, exactly. CRISPR, the gene editing tool, well, this latest version offers even better accuracy, more control.
Right.
And the potential there for tackling genetic disorders, things like sickle cell, cystic fibrosis, muscular dystrophy, it's just immense. We're talking about potentially correcting the faulty genes themselves.
It really is like science fiction becoming fact. And cancer research feels the same way. I mean, mRNA vaccine trials for lung, breast, pancreatic cancer.
It's a completely different strategy, isn't it?
Yeah.
Harnessing the body's own immune system, training it, essentially, to recognize and attack the cancer cells.
Which could mean more specific targeting and maybe hopefully fewer harsh side effects than traditional treatments.
That's the hope.
Yeah.
And alongside vaccines, you have these incredibly precise, targeted therapies. The NCI, the National Cancer Institute, they have a new CAR-T therapy.
CAR-T, right. Modifying the patient's own immune cells.
Exactly. This one targets a protein called GPC2 in neuroblastoma. Early signs and preclinical studies look promising.
Wow.
And there's similar targeted work from St. Jude's on pediatric medulloblastoma, focusing on the ELP1 gene and inhibiting another protein, MDM2, to restore a tumor suppressor.
It's like finding the specific keys to unlock these cancers.
Yeah.
And speaking of finding things, AI, artificial intelligence, it's making huge waves in medicine too.
Oh, definitely.
These AI-powered blood tests detecting over 50 types of cancer early. That sounds like a genuine game changer for diagnosis.
Absolutely. Early detection is so often the key, isn't it? AI can analyze these massive data sets. Spot patterns may be too subtle for the human eye. It could dramatically improve our diagnostic power.
And it's not just diagnosis. What about drug discovery? That AI model from Notre Dame, the conditional randomized transformer, CRT.
Right, the CRT model. It's designed to speed up that incredibly complex process of finding new drug candidates.
Which traditionally takes forever and costs a fortune, like finding a needle in a haystack.
Exactly. AI, like CRT, can predict how molecules might interact with disease targets, helping researchers focus their efforts much more effectively.
And then there's this AI chip smaller than a grain of salt, decoding images super fast using almost no energy. What are the possibilities there for, say, medical imaging?
Well, think about more portable, maybe even bedside imaging devices. Low energy means potentially continuous monitoring, faster diagnoses, right at the point of care.
It's just evolving so fast. And regenerative medicine, too. Bioprinting functioning organs, kidneys, livers, that felt like pure sci-fi just a few years back.
It's a truly remarkable achievement, though still early days, of course. But the potential to tackle the organ shortage crisis is just enormous. It could save so many lives down the line.
And artificial skin made from living cells. From researchers at Mass General, MIT, Shriners, that's huge for burn patients.
Treating living skin, yes. It can mimic natural skin functions better, potentially improving healing, reducing scarring. A massive step forward.
And there's so much else. Quickly, small molecule inhibitors for cytokine storms from Greenwich Uni, Nornova's NASH therapeutic, CRISPR refining precision medicine, telehealth expanding access, wearables tracking health, and St. Jude's work on targeting drug breakdown. It's just a flood of innovation.
It really highlights the sheer breadth and dynamism of medical research right now. Every single one of those holds real potential.
Okay, let's shift gears completely. Look outwards to space.
Yeah.
What are the cosmic discoveries that have really stood out?
Well, finding 128 new moons around Saturn was pretty extraordinary. Using that shift and stack technique.
128. That puts Saturn way ahead of Jupiter now, right?
Wow.
274 moons in total. That's right, 274. It really reshapes our view of Saturn's system, how it captured or formed all these smaller bodies. It tells us a lot about planetary formation.
Wow. Makes you wonder what else is hiding out there. And the James Webb Space Telescope and Tetra, they just keep finding more exoplanets, Earth-like ones in habitable zones.
They do. The ability to find planets similar to Earth, orbiting at the right distance for liquid water, it's a huge step in the search for life beyond Earth.
The ultimate cosmic treasure hunt. And then the hints. The possible signs of life in Venus's atmosphere, that's got to be incredibly tantalizing.
It is profoundly exciting. I mean, it needs much more investigation, obviously, but if confirmed, well, it would revolutionize everything we think we know about where life can exist.
Mind-boggling.
And finding 3 new rocky exoplanets around Barnard's star, one of our closest neighbors, it just adds to the richness of our local galactic neighborhood. It feels like we're building this amazing catalog of other worlds, and those super detailed images of a black hole. What new things are we learning from seeing them that clearly?
Well, the unprecedented resolution lets us study the event horizon, the accretion disk, with much greater precision. We can test Einstein's theories in these extreme environments, learn how black holes grow, how they influence galaxies.
That's wild. And finding oxygen in the most distant known galaxy, JD's GS-Z14-0, that's like looking back to the universe's infancy.
Exactly. Finding oxygen that early on, just a few 100 million years after the Big Bang, tells us crucial things about the first stars and how they started enriching the universe with heavier elements.
Closer to home, the Parker Solar Probe actually flying through the sun's corona.
Yes, directly observing it. It's giving us invaluable data on solar wind, flares, the fundamental processes driving our sun, which impacts space weather, impacts us here.
And confirming auroras on Neptune, using Hubble and Webb together. Even the ice giants have those light shows.
It expands our understanding of their magnetic fields, their atmospheres. Using both telescopes gives a much fuller picture across different wavelengths.
Okay, shifting scales again, dramatically. From the vastness of space down to the quantum realm and new materials, quantum computing. It really feels like it's moving from theory to, well, something more tangible.
It does. Major tech companies are making platforms more accessible, investing heavily. It signals a real acceleration.
And OpenAI's GPT 4.5 preview, the hint that it might be tapping into quantum computing, that sounds like it could be a massive jump for AI power.
Well, if quantum can be effectively integrated with advanced AI, yes, it could unlock breakthroughs on incredibly complex problems, optimization, materials design, simulations. But it's important to remember that's still very much in the research phase.
Right. But concrete steps are happening, like the Ocelot chip from AWS and Caltech. Using cat qubits to cut down errors, that seems critical.
Oh, absolutely critical. Qubits are notoriously fragile. Error correction is a massive hurdle. Developing more stable qubits like these cat qubits, which are inherently more resistant to certain errors, is a vital step towards practical quantum computers.
Makes you appreciate the groundwork, like Peter Shor's algorithm showing quantum's potential to break encryption.
Indeed. Shor's algorithm was pivotal. It highlighted the disruptive power and really spurred a lot of the research we see now.
And fitting that the UN declared 2025 the International Year of Quantum Science and Technology.
It underscores the global significance, aims to raise awareness, and foster collaboration in this fast-moving field.
We mentioned that tiny AI chip earlier. Its energy efficiency could also be important for quantum communication, couldn't it? Secure data transmission.
That's a good point, yes. Highly efficient components like that could be crucial for building the infrastructure needed for quantum networks.
Okay, materials. Lots happening in sustainable materials, which is encouraging, like Grastic from UBC, recyclable water-based adhesives, biodegradable bioplastics.
It reflects that global push, doesn't it? Developing materials that work well, but also minimize environmental harm. Moving towards a more circular economy.
And those frameworks, MOFs and COFs, metal organic frameworks. Covalent organic frameworks. Their applications seem almost endless. They have these tunable structures, right?
Exactly. They're like microscopic scaffolding with huge surface areas inside. You can tailor them for so many things, storing gases like hydrogen, capturing CO2, catalyzing reactions, even delivering drugs.
And Maxwell Labs using lasers for cooling computer chips. Photonic cooling, that seems vital as chips get hotter and hotter.
It's a critical challenge, managing heat. Photonic cooling offers a potentially more effective, maybe more energy efficient, alternative to traditional fans and heat sinks.
I was also intrigued by generating electricity from falling rainwater. Just a neat idea, finding energy in unexpected places.
It's a fascinating concept, exploring an untapped source. Maybe not huge amounts of power, but it shows real ingenuity.
And briefly, those fundamental physics updates limits on dark matter, refining the strong nuclear force theory. They might seem abstract, but they're crucial, right?
Absolutely. They form the bedrock for future understanding, future tech. They push the boundaries.
And the Breakthrough Prize for the LHC experiments at CERN, a well-deserved recognition for that massive international effort.
The LHC continues to be at the forefront of particle physics, giving us profound insights into matter and forces.
Okay, let's zoom in on biology now. What are the biological breakthroughs that have caught your eye?
Well, the CRISPR story just keeps unfolding. It seems its gene editing capabilities are even more versatile than we first thought.
Right. Every time you think you've got a handle on it, researchers find a new application, and the therapies based on it are multiplying.
For inherited disorders, cancers, even improving crops, CRISPR is proving incredibly adaptable and powerful.
And the gut microbiome feels like we're just scratching the surface of how those trillions of microbes affect our health.
That's absolutely right. They play huge roles in digestion, immunity, even brain function. Research there could lead to new therapies using probiotics, prebiotics, manipulating that ecosystem.
Discovering a new class of anti-malaria antibodies, that's massively important too, given drug resistance.
It is. Finding new ways to fight malaria is urgent, and these novel antibodies offer a really promising path for next-gen treatments.
I was really interested in those fetus cells, playing a role in suppressing inflammatory responses to food. Could that be a key to understanding childhood food allergies?
It could be. Understanding the mechanism is crucial, and identifying these specific cells gives researchers a new target for potential treatments or preventative strategies for these often really debilitating allergies.
And on a lighter note, finding the specific gene for orange cats, sometimes it's the smaller puzzles that are just fun to solve.
It's a great illustration of how genetics unravels the world, even seemingly simple things, and, useful pub quiz knowledge.
Huh, true. And we're seeing more use of organoids, those mini lab-grown organs, like St. Jude's using a cortical organoid, a mini brain model, to study epilepsy.
Yes, organoids offer a much more physiologically relevant way to study diseases compared to standard cell cultures, or maybe even some animal models. It can really speed up discovery and testing of treatments for neurological conditions.
And finally, using those plastic-eating bacteria, like Ideonella sacaiensis, more efficiently for recycling. Biology tackling environmental problems.
Harnessing biological systems like that offers a really sustainable, potentially very effective way to deal with the massive plastic waste problem.
Okay, let's pivot to pure technology now. AI, robotics, energy. What are the big transformations happening on that front?
Well, the talk around general AI continues to build, and the development of what's being called the first fully autonomous AI robot scientist. That's a pretty significant marker.
An AI that can design and run its own experiments, make discoveries. That sounds potentially revolutionary for the speed of science itself.
It certainly holds that potential. And you see AI becoming more woven into daily life, too, like those AI-monitored fridges that supposedly build your grocery list.
Right. It's becoming a less of a distinct tool and more just part of the background fabric. And brain-computer interfaces, BCIs, Neuralink enabling paralyzed patients to control devices with thought. That's just profound.
Truly life-altering potential there. Restoring lost function, improving quality of life for people with paralysis or other neurological issues. It's incredible progress.
We mentioned quantum computing earlier with physics, but its tech impact bears repeating breaking encryption, accelerating drug discovery.
Absolutely. It's a foundational tech shift with the power to remake multiple sectors. Its development is a huge focus.
And energy. Solar and wind becoming dominant, plus green hydrogen emerging as a viable, clean fuel. Feels like real momentum towards sustainable energy.
The costs keep coming down for renewables, efficiency goes up, and producing hydrogen cleanly using renewables. That's a crucial piece of the puzzle for decarbonizing.
And solid-state batteries, that could be a genuine game changer for electric vehicles, right? And grid storage, what's the key advantage?
They replace the liquid electrolyte in current batteries with a solid. That potentially means better safety, higher energy density, more range for EVs, faster charging, longer life. Very attractive tech.
The metaverse, still a bit fuzzy for many, I think, but the potential to change how we interact online seems huge.
It could fundamentally reshape socializing, work, learning, entertainment,
Yeah.
creating much more immersive digital spaces.
And that e-taste device, digitally simulating taste. That sounds wild. Imagine adding that to VR or AR training entertainment.
Yeah, simulating taste could open up all sorts of new applications.
Right.
Enhanced gaming, realistic training sims, maybe even helping with dietary management.
And just looping back quickly, that laser cooling for chips and the rainwater electricity. Key tech advances, too.
Important steps in managing computing's energy demands and just exploring novel energy sources.
Now let's tackle the elephant in the room sometimes. Research funding. It sounds like there are some really significant shifts happening there.
Yes, quite significant. The proposed federal budget cuts we've seen reported for agencies like the NSF, NASA Science, the NIH, they're substantial.
We're talking potentially huge percentage drops, 56% for NSF, 46% for NASA Science, 37% for NIH. Those are massive numbers.
They are. Cuts of that magnitude could really impact the number of research projects funded, fewer grants awarded, potentially slowing down the pace of discovery across many fields.
And it's not just proposed cuts. There have been actual policy changes, like the Department of Energy capping indirect cost rates on grants.
That's right. And it mirrors a similar move proposed for NIH that was blocked earlier. Universities are very concerned.
Why? What do those indirect costs actually cover? It's not just slush funds, right?
No, not at all. Indirect costs cover the essential overhead of doing research, maintaining labs, utilities, administration, regulatory compliance, IT infrastructure. Capping them puts a real strain on universities' ability to support the research itself.
And the reports about funding freezes to specific universities like Harvard under the previous administration. That feels like politics directly influencing funding decisions.
It certainly raises concerns about non-scientific factors potentially playing a role in funding allocation, which ideally should be based purely on scientific merit and potential impact.
What about the priorities outlined in that Project 2025 report? It suggests maybe more focus on fundamental research at DOE, but specific applied areas like AI, quantum, fusion at NSF and DOE.
The report does suggest a potential recalibration, yes, possibly emphasizing basic research in some areas while strategically targeting others seen as national priorities, AI, quantum, fusion, critical minerals, those sorts of things.
And the NSF actually terminating grants related to DEI, diversity, equity, and inclusion, and combating misinformation. That's a clear policy shift.
It definitely signals a change in the types of research and activities the NSF will prioritize for funding going forward.
Looking bigger picture, there's that long-term trend of federal R&D funding declining as a share of GDP, with the private sector picking up more slack. What does that imply?
Well, it could mean a growing emphasis on research with clearer near-term commercial payoffs. Potentially less support for the kind of fundamental, curiosity-driven research that might not have immediate market value, but can lead to massive breakthroughs down the road.
But we should remember, private foundations are still crucial players, right? American Cancer Society, Robert Wood Johnson, Spencer Chan Zuckerberg Initiative.
Absolutely vital. Philanthropy provides essential funding across many areas, often filling gaps left by federal limitations. They're key to the whole ecosystem's health.
So with these potential federal cuts, what are the broader worries for U.S. science? You mentioned Harvard and Northwestern looking at self-funding more. Is that sustainable?
The consequences could be pretty significant. A potential slowdown in discovery, maybe losing competitiveness in some fields, challenges attracting and keeping top scientists, self-funding. Well, it highlights the pressure, but it's probably not a universally sustainable fix.
But it's not all doom and gloom. There are still specific opportunities, like the DOE's early career program, other NSF initiatives.
That's correct. While the overall landscape might be tougher, specific programs supporting researchers, especially early career ones, and in targeted priority areas, do still exist.
Okay, let's shift to the policy and political side shaping all this. What are the key policy changes, the legislation we should be aware of?
Well, one big one is Executive Order 42179 on AI. It revoked a previous order, signaling perhaps a more deregulatory approach.
Aiming to spur innovation faster by reducing government oversight, maybe?
That seems to be the intention, yes. Fostering innovation, maintaining U.S. leadership. There was also a separate order focused on improving biosafety and biosecurity.
And legislatively, April 2025 seemed busy. The No Fakes Act, Delete Act, AI Workforce Stuff, Healthy Technology Act, Immersive Technology, quite a mix.
It really is. It shows policymakers are grappling with the wide impact of tech, from AI's creative implications to workforce needs to regulating new digital environments.
But interesting that there's still some bipartisan support for things like the Keep STEM Talent Act, the American Innovation Act, suggests some common ground remains.
Yes, despite disagreements elsewhere, there often is a shared understanding that supporting STEM talent and innovation is crucial for the country's competitiveness and tackling big challenges.
We mentioned the NSF actions ending DI misinformation grants, reported executive RESSFs, eliminating the equity division. Those are concrete policy shifts within the agency.
They clearly indicate changes in NSF's strategic direction and structure under the current environment. And similarly, that NIH policy change on not renewing international subawards for health research.
Right. Restricting funding for international partnerships, that could really affect global health collaborations involving the U.S.
It likely makes institutions more cautious about initiating or continuing those kinds of collaborations when they're the prime grant holder.
And what are the administration's sort of stated overarching S&T policy goals?
The stated priorities generally focus on maintaining American leadership in critical technologies, promoting domestic innovation, and protecting U.S. tech assets and IP from, foreign exploitation.
And we're seeing states get more involved too, right? Like Montana's Right to Compute Act regarding AI.
That's right. As tech like AI becomes more pervasive, different levels of government are starting to explore how to legislate or regulate around it.
Okay, putting it all together, the progress, the funding shifts, the policy changes. What are the biggest challenges or threats facing U.S. science right now?
Well, the funding uncertainty is definitely a major one. The proposed cuts, the indirect cost caps, it creates instability, makes long-term planning really hard.
Yeah, that climate of instability must be tough for ambitious long-term projects. And concerns about political interference, potential censorship, that strikes at the heart of scientific integrity.
Absolutely. Maintaining objectivity is paramount. Any hint of interference erodes trust and hinders progress. The rescinding of the NIH scientific integrity policy, for instance, was concerning to many scientists.
Research security is another big theme. More scrutiny on international collaboration, restrictions. How's that playing out?
Well, while security concerns are legitimate, the increased scrutiny can definitely create barriers. It can slow down the free exchange of ideas that science thrives on. The reported distrust around collaborations with China, for example, is a significant factor.
And challenges to academic freedom, inclusion, with executive orders, policy changes limiting DEI research, the NSF actions.
Those changes can potentially stifle important research on societal issues and maybe limit the diversity of perspectives within science, which is actually crucial for innovation.
And it's worrying to hear reports about talented U.S. scientists thinking about leaving the country or even the field entirely. That brain drain risk.
It's a real concern. That combination of funding uncertainty, maybe perceived political headwinds, a potentially less welcoming environment, it could push talent away. A huge loss.
And finally, those partisan splits in public trust in scientists, plus misinformation. That's a tough challenge for the long-term health of science support.
Maintaining public trust is vital. For funding, for accepting evidence-based policies, combating misinformation and bridging those divides is critical.
But okay, despite all those challenges, there are still incredibly exciting opportunities ahead for U.S. science. Let's end on those. AI and machine learning, for starters.
Oh, the potential is just immense. Healthcare transformation diagnosis, drug discovery, personalized medicine, but also automation, finance, transport, the development of neuromorphic computing, mimicking the brain. That's another exciting frontier.
And quantum computing, despite the hurdles, the potential applications are just revolutionary.
Photography, materials science, pharma development. Quantum promises to solve problems completely beyond today's supercomputers.
Biotechnology, synthetic biology too.
Yeah.
Huge innovation potential.
CRISPR keeps evolving. Gene therapies are expanding. And synthetic biology engineering biological systems offers sustainable ways to make pharmaceuticals, biofuels, advanced materials.
And sustainable materials and green tech are so crucial for climate change.
Definitely. Better batteries like solid state, more renewables, green hydrogen, biodegradable plastics, better recycling, all essential for a sustainable future.
Space exploration feels like it's entering a new era, too, with commercialization really taking off.
Yeah, long-term Mars ambitions, in-space manufacturing, growing private sector involvement. The opportunities in space are expanding rapidly.
And that push towards personalized precision medicine, tailoring treatments based on our individual makeup.
Using genomics, AI, wearables, it promises much more effective, targeted treatments and better patient outcomes.
Thinking about the broader impact now, science and tech have always been huge economic drivers for the U.S., haven't they?
Absolutely. A huge chunk of economic growth since World War II is linked to S&T advances. Federal research funding creates significant economic activity, jobs.
And the health impact is undeniable. New vaccines, like those mRNA cancer ones, gene therapies, AI diagnostics.
Real breakthroughs, improving public health, extending lives. The mRNA platform itself has shown such versatility.
And it's just woven into our daily lives now, isn't it? AI on our phones, autonomous vehicles coming, smart homes, telehealth.
Fundamentally reshaping how we communicate, work, live, access information.
And on the world stage, S&T leadership is critical for national security, global influence.
Maintaining that competitive edge in key technologies is a core focus for U.S. security and global standing.
What about how the public sees all this? It sounds like a mixed bag.
It is complex.
Yeah.
Generally, a majority trust scientists, but there are definite partisan divides. Encouragingly, though, there's broad support for government investment in STEM education.
And lots of efforts seem underway to bridge the gap between science and the public.
Yes, scientific societies, national academies, museums, universities, government agencies, training programs, all working on better communication and engagement.
It's interesting, though, how public perception of AI differs from the experts. More public concern about jobs, losing human connection, highlights the need for clear communication.
Absolutely crucial. Clear, transparent communication builds trust and helps society navigate the implications, both good and challenging, of new tech.
And lastly, international collaboration. It sounds like a more challenging environment now for U.S. scientists working globally.
It is. Budget issues, visa hurdles, the intense focus on research security, it's creating headwinds. That NIH policy on international subwords, the reported concerns about China collaborations, they illustrate the trend.
But efforts to collaborate continue because science is global.
Yes. Despite the challenges, organizations, universities, consortia are still actively fostering cross-border science. There are many examples of ongoing partnerships, but that increased focus on security and disclosure requirements is definitely shaping how those collaborations happen.
Well, this has been an incredibly thorough deep dive. Pulling it all together, it feels like a time of amazing scientific leaps forward.
Truly remarkable progress across so many fields.
But happening against this backdrop of really significant shifts in funding and policy.
That's a good summary. And the potential of these emerging fields, AI, quantum, biotech, is just undeniable. Huge promise for tackling big global challenges.
But realizing that potential, that's going to take sustained investment, right?
Yeah.
And a supportive policy environment, one that encourages innovation but also responsible collaboration.
Precisely. How these incredible discoveries interact with the changing funding and policy world. That's what will really shape the future of innovation and America's role in it.
So maybe the question for you, our listener, is this: how will that dynamic, that interplay between discovery and the system supporting it ultimately shape the future and maybe shape your own life? Definitely something to think about. Thanks for joining us on The Deep Dive.